You believe it's halfway through the semester?
Yeah, that's one of the best.
It's flying. All right, so here is this sketch. Move this down. Move this. And just to kind of review, if we took the control volume, and you don't draw this because I'll draw this. Say we picked our control volume like that, the dotted black. Down here, what would you have down here?
Down by the
Down by the where it's hooked in there. Yeah, you could have
a fixed support.
like let's call this point B. So you could have BY. Oops. Let me do that in a different color. Green. This could be BY. Oh, that's not going to work. You could have BX. What else acts down there?
Moment.
There would be a moment, but also you have
Oh, your gauge pressure.
PB gauge times AB.
But that would cancel out because it's going atmospheric.
Not right here.
Oh,
Not inside the pipe. That's pressurized. Yep.
Define that as
Yep. Yep.
We'll see because it's.
Well, this is just kind of actually going to help you for problem one. This isn't
That's
what we're
what I'm
going to do
saying.
for this one. Yeah. Then we have this would be coming in maybe 0.1, and this is 0.2,
Essentially.
and this is P2 gauge A2. But that's atmosphere, right? And that goes away. And actually, atmosphere acts all over this whole control volume, but they all cancel. All right. So these are the reaction forces needed to hold it down. There would be a moment down here, which would be MB. And this is everything that you kind of would need to do for problem one in your homework. Okay, it's a fire hydrant with stuff sticking out horizontal on one side and it's shooting out at an angle on the other side. Okay, so they want you to figure out the moment at B. All right, and find the reaction forces. So always remember, we also have weight, right? A weight force. I think the homework neglected it. Yep. So you have body forces, which is weight. You have surface forces, which are pressure. Okay, and then you have reaction forces. That's all the time when you have this stuff. Why do we need to know these forces, By and Bx? To size the bolts or to figure out how much weld you would need to hold it in there, right? The pipe. Also, what about moments? Well, the moments you could figure out how thick the steel needs to be, the tubing needs to be in order to hold that moment there. And again, moment you could use for the bolt sizing too, right? Okay. So if this is fluid moving, you do momentum analysis like we did. Okay. So you do sum of the forces equals summation of m dot v. What was it? In or out?
Out.
Out. Okay. It's slightly different for thermal. And I just skipped the MA term just for now.
But aren't we trying to find horizontal and vertical?
Yeah, so there's going to be two. The forces, there's two components. In this, then you could also find a moment, right? And this moment is summation of m dot v times r out minus summation of m dot v times r in. So those are the two fundamental equations that you would use to figure out forces or moments for linear momentum of fluid. Okay? So that's intermediate fluids. In fluids, what do you think we would find in regular fluids? And
Mass flow rate.
we could, well, yeah, mass flow rates, volumetric flow rates. Also, it shoots up here, like how much of a pump you would need to shoot it up 3 meters in through this piping. So what do you lose? What's happening as the water goes through this pipe? Friction in the piping, yep, which you got to overcome. Remember, that's the minor losses. And you have major losses. So major losses is the pipe friction. The minors are the elbows. Okay, so you can figure out the pump sizes. Again, figure out overcome gravity for shooting straight up. What happens then if the temperature is like 70 degrees here and it shoots out to 20 here? What course does that involve? Thermal. Okay, so use energy balance, which is thermodynamics, and you can figure out, again, you could also then use that to figure out pump sizing too, which is the same thing, or efficiencies, okay? So just to give you an idea where all these courses fit, they all fit. We just do bits and pieces of each course, and then you can apply them later on, okay? All right, so this will help you for the homework. Let's now figure out what the moment at A would be. So we're going to sum the moment at A. So we have m dot v times r out minus summation of m dot v r in. So on the left, that's what we're looking for. So we're just looking for m dot A. So what happens to all this stuff in the bottom left? And don't worry about this moment. But what happens to all these forces here? This By goes away because it's in the line of action. And this right here, same thing, line of action. And I believe when you figure this out, there's no force in the x. Because Bx is 0, so that doesn't even show up. Okay? But say there was, this was shooting at an angle. Would there be?
Yeah.
Yes. Then you would have to figure out what that force is and then multiply by that 3 meters. Okay? So the only two forces we have are weight, and we have the right-hand side over here. Okay? So, whoops, I didn't want to do that. Yep. Yep. So I'm going to keep. I don't like how they did it. Okay. So we have MA. Then we have forces. And which way do you want your positive direction? Clockwise or counterclockwise? Clockwise? Okay, we'll pick clockwise. Doesn't really matter, right? So that's why our MA is positive. So let's do that. Then we have plus W times what? What's R1? Yep. So I'm going to do 2 meters over 2 because that acts halfway. And we have a positive moment. The other force would be this gauge, right? That one's 0. It's the atmosphere, so we don't have to worry about that. Now there's no other forces or moments. Equals. The in term, like you said, goes away, right? So we have, this would also be a what? Positive moment. So we have m dot 2 v2 times 2.
Isn't MDOT just 15?
What else? Water discharges, so 7 meters per second. Do we know, what do we know?
It's 15.
Oh, we know the diameter, so we can figure that out. Okay, so let's just solve for MA. So we have m dot 2 V2 times 2 meters minus W times 1 meter. And I'll write it all in here. So m dot we know is rho AV times V2 times 2 minus, and the weight is M times, oh, that should be, how long is that section? 2 meters?
Yeah.
Actually, let me put the units in. So it's 15 kilograms per meter, and the whole pipe is 2 meters, times by 9.81 meters per second squared, times 1 meter. I'm kind of breaking my rules, but I'm fine now if you put numbers in like this. Again, the weight was 15 kilograms per meter. The whole length of that is 2 meters. Multiply by 9.81, that gives you the whole weight in that section. But that weight force only acts 1 meter away from that. Okay, and let's finish this. 1,000 kilograms per meter cubed times pi times 0.15 squared over 4. And those are meters, right? Squared times 7 meters per second. And I'm going to square that times 2 minus, and I'll just put these numbers here. If you have a calculator, just check this for me. My guess is going to be positive 1438 Newton meter. Yeah, because it's V2 in the mass flow rate, and then it's multiplied by the velocity. Yep, that's why I squared it. So it would be 7 meters per second times 7 meters per second. Yeah, this term over here comes, what, 294 something? 294.3. No, didn't come out?
Yeah, I found one. No, come on.
Yeah, just
I'll see what you want.
Yeah.
yeah.
Water was going out fast enough at the moment. I could go that way instead. Yeah, we don't do it.
1437, okay.
No way, yeah.
The water's going out quick enough, why wouldn't the force be acting upward and it would hold it down right here?
You're looking at
Why
the
would I
velocity.
wanna go this way instead?
No, exactly. That's what I was thinking.
So like if there was nothing happening to it, I would think that the moment I would want to go the way that you are going, but since you are
I didn't.
having forces acting downward, I feel like the moment needs to be
Oh.
in the opposite direction.
It's, so the water's shooting out, so this does want to go this way.
Right.
At the moment, it's going backwards to hold it there.
So there's two technically, right? One, when there's no water in it, it will want to go this way.
No.
and then
No,
when-
it's always counteracting how it would be.
So the moment is, think of the moment of, is the pipe resisting that force up.
Yeah, yep,
Okay.
yep. Yeah, so if there was no water, this would, well, yeah, maybe it would go the other way, because it would be falling down, right? If there was no water, but now it's shooting out, this wants to bend this way, but it's holding, that moment's holding it there.
Okay.
Yep. Yep. Now, if we flip it, that's the second part. What happens if it shoots upward now? The water shooting up, what does this want to do? It wants to go down, so this moment should really be the other way. Okay? And it does, so watch. When we do this, we get MA equals this term. The term is the same. So this is our fundamental equation right there. So let me just write m dot 2 v2 times 2 meters minus w times 1 meter. So this part right here, now we have this goes up, over, and then shoots up. And we're doing the moment here. If we picked our direction, which way did I have MA? To go this way, this is shooting out. What does that create now for the mass flow rate times V dot? That's going around this way, which creates a negative term. So now you have a negative minus a negative. You're going to get a negative, indicating that this should actually go that way. Okay, which makes sense because it's shooting up, it's pushing it down. It's the resistance force to hold it the other way. Yep. And this comes out to be negative 2026 Newton meter. Okay. Well, it's more because it's adding with the weight. Isn't that crazy? Yep. Yep. Which makes sense because it's shooting up, it's pushing that beam down, and it's the same as if there was no water, it would sag down. So cool, right? I mean, next time you look at a fire hydrant, which is your problem one, you'll be like, oh my God, water's shooting out. You're going to be thinking of all this stuff in your head. Like, there's a moment created at the bottom. Look at the size of the bolts. Right? Most of the time, you don't worry about water flowing through stuff, right? The machine design or strengths. It's okay. Design the bolts. Well, now you have to worry about it in these cases sometimes. Okay. Questions on this? This should help you with problem one. Problem two in your homework. What's the fundamental equation for acceleration? dv dt. Yep. Okay. What is the fundamental equation for v? ds dt. Okay. Just remember those. Okay. Because you're going to use this. I think it's a girl skating. She's got a hose. Okay. We're going to assume there's no forces acting on her. And she's moving. And there's only like one term out. There's nothing coming in at her. So you eventually end up getting this right here. So you solve for your acceleration. And then you use these fundamental equations to figure out what you need to do. Okay. Just get a little refresher of dynamics and intermediate fluid mechanics. What in that problem, your velocity is a constant number. Like say it's 10 meters per second. What happens if I told you that the water coming out of there is a function of time? Do the same thing. You just plug it in there, but your acceleration is a function of time. And so when you do this, when you integrate, you just have to integrate that with respect to time. Okay? So for example, let's say that V2 is 2t squared. Technically, if we rearrange this, I think one of these terms, I actually think, oh, this is plus, but I think this would come negative because it's going out the opposite direction she's moving. That's how you get a positive acceleration. You would end up getting rho A V2 times V2 over the mass. Once you rearrange that equation, if I substituted what mass flow rate was. If you plug this in, you'd get 2t squared times 2t squared over the mass. this becomes 4t to the fourth, right? Times some number,